Hello everyone, welcome back to the channel. Today we are going to break down one of the most important topics in biopharmaceutics and pharmacokinetics, that is the two-compartment model for an IV bolus dose. Let's start from the basics. What is a two-compartment model? Alright, imagine your body is divided into two boxes. Okay, first one is central compartment and the second one is peripheral compartment. Now this central compartment includes blood, heart, liver, kidneys and all the organs that get drug supply fast. Peripheral compartment. This is made up of tissues and organs that receive drug slowly. Now when we inject a drug directly into the bloodstream, that is an IV bolus, it does not just stay there. It starts moving. First distribution throughout the body, okay, then it begins to eliminate, and that's what the two compartment model explains perfectly. So central compartment and peripheral compartment, we have two boxes here which represent as CC1 and PC2. This model is used to describe pharmacokinetics of drug that shows distribution and elimination phases after an IV bolus dose. Let's understand the journey of drug in phases. We have three phases. First one is distributive phase. Right after the IV injection, the drug concentration in the blood, that is central compartment, drops very fast. Okay, why? Because the drug is rapidly spreading into the peripheral compartment. This rapid fall is known as the distribution phase. Okay, now second one, we have pseudo distribution equilibrium. After a short time, both compartments balance out. The drug is evenly spread. This steady state is called as pseudo-equilibrium. The distribution slows down here. Third one, we have post-distribution elimination phase. Now the drug is eliminated slowly from the central compartment, mostly by liver metabolism or kidney filtration. This phase is slower and it is called as the elimination phase. Now the drug is moving from central compartment to peripheral compartment to central compartment. So what gives the drug moving? The drug movement is guided by three rate constants. First one is K12, that is distribution rate constant from central compartment to peripheral compartment. Then second one is K21, that is distribution rate constant from peripheral compartment to central compartment. Then we have the Ke, elimination rate constant from central compartment. These constants define how fast the drug distributes and gets eliminated. Now let's get into the calculation part. Don't worry about it, we'll keep it simple. We want to find out how does the concentration of drug change in each compartment over time. So drug concentration in two compartments we have to find out. First one, we are taking the central compartment. Here you can see. So central compartment rate of change is equals to dCC by dt. Remember this. Okay, in central compartment. C here is because of central compartment. Okay, with respect to time. So it is equal to rate in minus rate out. See, what is rate in? K21, K21 from CP or PC, from peripheral compartment. Okay, rate in, it is our rate in. Then rate out minus rate out. Rate out is C K12 CC is going out. Okay, from here it is going out. And the other one is KECC is also going out. So minus. So rate in minus rate out. Remember this logic. For the peripheral compartment, rate of change is equals to dCP by dt, which is equals to rate in minus rate out. So you can imagine rate in minus rate out with respect to the diagram which I have shown. So it is for peripheral compartment. For the peripheral compartment, drug is coming from the central compartment, which is known as rate in. Now drug is going out of the peripheral compartment, so which is known as rate out. And lastly, the elimination part, where the elimination rate is typically first order and represented by dCC by dt, because elimination is from the central compartment only. So here we are taking KECC only. Why we are not taking rate in minus rate out? You can imagine a trash can, okay, a dustbin, where we can throw the dust, where we can throw the drug. We cannot take it back from the dustbin. So it's like that. The drug gets eliminated for completely. It is not a reversible process. So we are taking only KE, which is elimination rate constant. Now we have the drug concentration over time, which is mathematical expressions. After solving the differential equations, we get for central compartment. Okay, for central compartment we'll get Cc equals to x naught divided by Vc, then in the brackets K21 minus alpha divided by beta minus alpha e power minus alpha t plus K21 minus beta divided by alpha minus beta e power minus beta t. These equations you have to remember. Okay, remember these equations. There is a easy trick you can use it. See, when you are writing alpha here, you will get alpha here also. Okay, but in the denominator you will get beta minus alpha. When alpha is here, you have to take beta here. When alpha is here on the right hand side, you have to take alpha only. Then here, when is beta is here, so you have to take the same. Okay, same constant, that is beta. Then in the denominator you have to take the opposite one. Hope you are getting this. And where the x naught equals to bolus dose, Vc is the volume of central compartment, then alpha and beta are the distribution and elimination rate constant. For the peripheral compartment, Cp equals to x naught divided by Vc, then in brackets K21 minus alpha divided by beta minus alpha e power minus alpha t plus K21 divided by alpha minus beta e power minus beta t. Okay, remember with the same logic. Okay, and here we have where K21 equals to first order distribution rate constant from central to peripheral compartment. Please remember these equations. Now we have to see some important relationships between hybrid and micro constants. Alpha and beta are the hybrid constants and rest of all these are micro constants. So sum of this rate constants, that is alpha and beta equals to alpha plus beta equals to K12 plus K21 plus Ke, and the product of rate constants, that is alpha into beta equals to K21 into Ke. These relationships Okay, experimental hybrid values into, so this converts experimental hybrid values into actual physiological micro constants. It is very essential for calculating the drug elimination and distribution. Now we have the final mathematical model. The concentration in the central compartment and peripheral compartment are governed by two exponential equations. Okay, so they describe the drugs distribution and elimination phases. First one, we have the central compartment. Okay, Cc equals to A into e power minus alpha t plus B into e power minus beta t. For the peripheral compartment, Cp equals to A apostrophe or A prime into e power minus alpha t plus B apostrophe or B prime into e power minus beta t, where A, B represent constants for distribution and elimination phases, and alpha and beta are the rate constants for distribution and elimination. Let's look at what graph would look like. The y-axis is the drug concentration, the x-axis is time. The graph shows a bi-exponential decline. Okay, first steep slope, that is distribution phase, then shallow slope, that is elimination phase. The curve helps us visually understand the two phases clearly. So let's wrap it up. The two-compartment model explains how the drug moves and get eliminated from different body parts. It shows two phases: fast distribution phase and slow, which is elimination phase. The drug leaves the body only through central compartment. We use rate constants and exponential equations to understand this model. Understanding this helps in dose calculation, timing and prediction of drug levels at any time of and at any point of time. And that's all for today's topic. If this video helped you, don't forget to like, subscribe and share with your friends. See you in the next video. Thanks for watching.